Good.
All right, so this, you get it?
I got 2.41.
2.41. All right, let's go ahead and see this. So I don't need this right here. First of all, 1 mole. That's a kind of a chemistry term, right? So just so you know, 1 mole of anything has Avogadro's. It's just a shorthand notation for saying you have Avogadro's number of that thing. Now, Avogadro's number is another kind of chemistry thing. What this means is that there are 6.022 times 10 to the 23rd of whatever the molecule number of molecules basically is this. Okay. And the reason why the mole gets used is, say that the atomic weight of hydrogen is 1, right? So if I had 1 mole of hydrogen atoms, that would be 1 gram. And so it's really the unit of conversion between the atomic mass unit and grams. Okay. So that's historically where it comes from, and it's useful. Okay, so let's go back and do this. So we added 50 joules, so Q is 50 joules is equal to C. Well, is this constant pressure or constant temperature?
Constant volume.
Or constant volume. Yeah. Yeah, it's constant volume, so I get 3/2 Boltzmann's constant times N, which is 6.022 times 10 to the 23rd times delta T. And I just wanted how much the temperature rose, right?
Mm-hmm.
So I'm going to call this delta T here. And I want to solve for this thing. So I take that 50 joules, divide by all of this stuff. See?
It's actually 2.49. The last time I used the other one, 5/2. So
Oh. This one?
yeah, I got 2.49. Multiplied all of it and then divided by 50. Oh no, 50 divided by. Sorry.
Yeah. So
4.01.
what did you get? 4.1.
Yeah.
Yeah, I got that.
Okay.
Cool.
I think that's more or less reasonable. This, by the way, should have been the 6.022 times 10 to the 23rd times his Boltzmann constant. That's the same thing as R, by the way, in chemistry.
Oh, okay.
1 mole times that.
Okay, does that make sense to everyone?
Mm-hmm.
It's pretty straightforward.
So why don't you have like the delta T in that equation then? Like
Which one?
3/2 kV times N.
Because this thing, and if I included it yesterday, that was a mistake. I didn't mean to. This is independent of temperature. The Q is C times that, the change in temperature. So if I
Oh,
include-
so that's the C basically?
Yeah, this is
Oh,
just
okay.
the C.
Okay, that
That's
makes
the heat
sense.
capacity.
Okay.
And so if I, for instance, added like 100 joules of energy and say the heat capacity was 1 degree, or 1 joule gave us 1 degree, I'd expect the temperature change to be 100 degrees. And if I had, if I include the temperature in the CP, then that would be, that would not be correct. So there should be a linear relation between Q and the temperature rise.
So is change in energy always equal to when work is not present?
Yeah.
Is always equal to CT?
The change, yeah, that's right.
Right. Okay.
Yeah, Q is equal to the change in energy when you don't have work.
Okay.
That makes sense?
Mhm.
And if you don't have any Q, then the change in energy is equal to the work. So, I mean, it's all this,
Okay, yeah.
all that comes from the Q is equal to delta E plus the work done by the substance, and that's that expression for the
Is it
first
minus?
law.
Is it minus W?
What's that?
Is it minus work?
No,
The
Plus
change in
was-
energy of the gas is equal to
Oh,
the heat added
plus.
minus.
minus the work done by the gas. And so if I rearrange that a little bit, I'll get up to here. And that's conservation of energy written in kind of standard thermodynamics way. All right, let's do another, let's generalize this to beyond gases, okay? The beautiful thing about thermodynamics and like energy conservation is that it really applies to everything. So it's beyond, whether it's a gas or a solid or a liquid, you still have energy conserved. The thing about solids and liquids, however, is they don't tend to expand a whole lot when you add heat. They have some thermal expansion, but it's nothing like a gas. So the work done on those liquids and solids when I add heat tends to be littler than it would be for a gas. Hence, you don't have, liquid inside the cylinders of your car engine, okay? Because it's hard to get those to expand a whole lot. So we are going to assume, just for the moment, that when I'm adding heat to a liquid or a solid, it really is not doing any work. The work, it does some due to thermal expansion, but it's not as much as it would be. It's a very small percentage of the total energy it has. So let's look at a situation that's pretty common. Let's say I have a beaker of, say, water. Get this. Water. And let's say that I added some sort of material in here. Okay? Let's say that this was at one temperature, T1, and let's call the water T2. And it just starts out like that. What tends to happen?
They're gonna be the same temperature.
No. Well, if the T1 was higher temperature,
Yeah, let's say T1 is bigger, is greater than T2.
then it will transfer heat to T2 until equilibrium happens.
That's right. So from experience, we see this, that if we have two things in contact that have different temperatures, heat flows from the higher temperature to the lower temperature until the temperatures are the same. So heat flows from higher temperature to lower temp until the temperatures are the same. Now, in actuality, this is the fact that heat only spontaneously flows from high temperature to low temperature. That's actually a way to write what's called the second law of thermodynamics, one of several different ways. But they're all equivalent. So that's almost an expression of what we call the second law of fluid dynamics, which is entropy increases. But heat will only flow, which we haven't talked about yet, but heat will only flow from higher temperature to lower temperature until they become equal. If I call the heat that flows out of T1 negative Q1, or Q1, I'll just call it Q1. This is the heat that flows from there. And the heat that flows to the water, Q2, heat from 1, heat to 2, actually heat to 1, and it'll be negative because heat's flowing from it. Heat to 2. What if energy is conserved? These two things have to be related, right? In fact, all the heat that flows from 1 going to 2, they should be equal to each other, shouldn't they? But negative in sign, because heat's flowing from 1 and to 2. So we can have that Q1 is equal to negative Q2.
Q2 will be positive, wouldn't it?
Q2 will be positive because heat's flowing to it. And so Q1 will then be negative because heat's flowing away from it. And we can just introduce really quickly, write those in terms of temperature change. Let's say that after some time, like this, after some time, all of these are at some final temperature. Okay, they've come to the same temperature. Then the change, then we could write that Q2 is going to be equal to C2, heat capacity of 2, times the change in temperature. That'd be T final minus T2. All right? And Q1 would be C1, T final minus T1. You see that? If this is just heat capacities. And so if we knew the heat capacities of these various substances, we could end up, and knew the initial temperatures, we could then get what the final temperature has to be. Does that make sense?
Is heat capacity like a given constant, or?
Well, I'm about to get to heat capacities, and we did heat capacities for gases, and actually they're sort of more complicated in many ways. When we're dealing with liquids and masses, these heat capacities, C's, are usually written in terms of what's called specific heat. All right, specific heat, anyone know what that is? That's the heat capacity per mass. So we take a mass, whatever the mass of the substance is, and then times what we call little c. Maybe I'll do it like that, little c. This is called the specific heat. And you'd have to look that up. That's different for every material. Depends on the material. So for instance, the specific heat of water, that one's pretty famous. Does anyone know what it is? So this specific heat of water, just call it like this. It's 1 calorie per gram per degree C. And calorie is 4.135 joules per gram per degree C. Okay. was I gonna remember that? Oh, 186. Sorry. This is one of the highest specific heats you'll ever see. For some reason, water is, it has a huge specific heat. You have to add a lot of heat of it to increase its temperature. Another example would be like iron. Specific heat of iron, solid iron. This turns to be about 0.4 joules per gram per degree C, roughly. And so these, so for instance, water's 10 times more than the specific heat of iron. All right, well, what are we going to do with all this? So this will tell us, given certain masses, given specific heats, you can now calculate these heat capacities. Given these heat capacities and initial temperatures, and knowing that these two are negatives of each other, you can then get that final temperature, right? So let's see if we can put all this together into a problem. So here's the problem. Let's say that, I'll just use this example, this picture. Let's say this is 100 grams of iron at 380 Kelvin. And this is 1 liter of water at 300 Kelvin to start out with. What's the final temperature? Go ahead and see if you can get that. By the way, how many grams is a liter of water? So milliliters the same as a cubic centimeter, and water had 1 gram per cubic centimeter. So this would be 1,000 cubic centimeters in a liter.
Some grams.
So done, right?
Yeah. You can work with the person next to you if you want. There's a fair amount of stuff to combine, but it's not too hard to picture. The C1 and C2 are the heat capacities, which are related, which are mass times specific heat. It's twice as much water. They have to add twice as much energy to heat it up.
Yeah. That's correct.
0.44.
Okay, so she will equals.
That's pretty bad looking.
There's 1,000 grains of paper.
So this is the specific, like this, by the gas. So for instance, if I have 1,000 grams of water, 2,000 grams of water, I have to add twice as much heat to the 2,000 grams of water to get the temperature to rise the 6 pounds. All right. Well, I started to think Q1 is maybe not Q2. Heat that flows. Well, first of all, there's the heat that flows. And it'll flow from the iron to the water. Okay. So the amount of heat that flows from the iron to the amount of heat into the water.
Yeah, it's trying to do it that way, but it's not. It's not
Okay.
So just write Q1 is equal to minus Q2. That's all it is. And you know what the Q's are. Substitute Q's in. Okay, those C's and the Q's are heat capacity. Those are the
How do you combine these?
Want this equal to the negative of this. And then all I did is I distributed this throughout, this throughout.
Oh, okay.
And whichever one I had negative, I took the negative with it.
Okay.
And then just solved for it.
What's QT? Oh, you don't really sell it. You can't really.
But as, well, as, we don't know what's going on.
Just he gave it to us. He gave us mass of the water.
Each other.
He's one later, so it's about.
He's going out of one and into the other.
Okay.
So only be 300.
I'll sit like that halfway there.
That's the change. That's why you say Q2 is equal to Q minus Q1. Solve for it. That'll be. Yeah. Well, the T final should, in both those equations, should be the same when they come to, because they come to the same final temperature.
Right.
So you can take it out, so like get both of them themselves, or all around one button and just take it out. And then if that's the case, like, it'll be a T final times like -3 times -3. What? Well, yeah, I was saying.
Is it all?
Right over here.
Yeah, looks good. Right, man. No.
Okay, so what up there?
One, maybe it's just
So would it be easier if I divided
So you have
this side
C1
by this
times
to get over here?
C1 delta T equals negative C2 delta T.
Oh, okay. Okay.
Well, no, I'm just shortening it, because it'd be really confusing to say that on one line.
Okay, who's getting who's getting an answer?
I don't know, but I don't know if it's right.
What did you get?
Yeah, 2 negative.
So you mean that the water temperature actually cooled off when I put that hot iron in it?
I get it. I have no idea. I don't know how to do it, so I just set them what I thought. I just set them equal to, like, so I set this one equal to the negative of the other.
Yeah, that's good.
And then after that, I
Wait.
distributed.
So you said them equal to it.
Oh, yeah. Okay, well.
Okay.
And then I distributed this through, and then this through, and then I subtracted. It might be in my signs, but like.
I think there's a minus sign, so you can.
So you got some fresh up the things, except optical.
Let's just calculate the
Oh.
Yeah, your one can't be true,
It's really hard to do.
just simply for the fact that I took one temperature, I took something hotter and put it in there,
And
and
it
then
doesn't
both of them
get-
froze.
That gives you.
You know?
Magic.
Got
I
cooler.
think it's doing the signs. Okay.
You guys get an answer?
Yeah. Seems like it'd be right. It's similar, if they have the same heat capacity, that would, so it's like, well, fine, I think something's gonna show up there. Heat up.
So did you multiply the specific heats by the masses? So 100 grams for the iron, 1,000 grams for the. You need to do what? So nice to. So you get the T by myself, good.
75 degrees. 300 degrees.
In this experiment. So, what I gotta do is factor out the T final. If that makes sense. All right, you guys ready?
Yeah.
Who got an answer? Anyone want to volunteer there? Yeah, what do you get?
300.8.
Nice. Good. Yes. Who got that, by the way? You can pretend. All right, so T final, let's check this. $8.3.
Yes.
All right, question mark.
Well,
So let's-
that's what I got.
Yeah, so let's make sure that, let's see how it goes. I'll start here and then we'll remember what our formula for heat capacities are. So these two have to be negatives of each other. The heat that flows from this hot iron to the water is going to be equal in magnitude to the heat that is gained by the water. It's just negative in sign. So the water gains heat, the iron loses heat. And so I can say that Q2, 2 is everything that says 2 is for the water, is equal to negative Q1. And I'm just going to substitute these things in. So I'm going to take these and just substitute it in. So I get C2. This is the heat capacity of the water, of the water, times T final minus the initial temperature of the water, T2, is equal to negative C1 T final minus the initial temperature of the iron. Let's put this minus sign through, like that. And I want to end up solving for T final. So here's where working algebraically until near the last steps really is nice. So I do C2 T final minus C2 T2 is equal to negative, or actually I can redistribute that through, negative C1 T final plus C1 T1. Everything that involves a T final, which is what I'm interested in, I'm going to bring over to one side, and everything not involving that, I'm going to keep on the other side. Uh-oh. All right, we go over here. Okay. So I'm going to have C2 final plus C1 T final is equal to C1 T1. Oh, I don't need this picture. Plus C2 T2, right?
Mhm. Now factor out a T.
I can factor out a T final from this. So I could write this as T final times C1 plus C2 is equal to C1 T1 plus C2 T2. Now divide through by this sum of the heat capacities. So T final is equal to C1 T1 plus C2 T2 over C1 plus C2. All right. So maybe you did that all numerically, but you know you didn't. And it's okay if you get the right answer. But I think that that's probably easier. Now we have to figure out what the heat capacities are. So C1, that's the heat capacity of the iron. That's going to be the mass of the iron times the specific heat of iron. So that'd be 100 grams times 0.44 joules per gram per degree C. So this would be 44 joules per degree C. Okay. C2, that's the heat capacity of water. That would be the mass of the water times the specific heat of the water. So if I have 1 liter of water, that's 1,000 grams. So 1,000 grams times 4.186 joules per gram per degree C. So that would be 4.186 joules per degree C. Okay, makes sense? I just substitute these things in, and then put for T1, put what is it, 380, and for T2, 300. And when I do that, I should get that 300.8. Does that make sense? You want to do another one? All right, one more. Or you guys see if you can get this one. It's okay if I erase this. I need some room. We can do it over here. All right. Now, sometimes it's pretty hard to measure temperature of a solid. You can do it, you can maybe find the outside temperature of it, but it's hard to kind of figure out an average temperature because, you know, you can't You can't put a thermometer inside of a solid, can you? Very easily. But one thing that you can do is do what we just did, sort of, and but now use the equations a little bit differently. So let's say I put a mass of iron. We'll use iron just so I know this, so because we know the specific heat roughly. Let's say that we put 100 grams of iron into a bath of water, 1 liter of water at 300 Kelvin. We'll keep all that the same. And let's say that T final turned out to be equal to 302 Kelvin. And you measured that. What was the temperature of the iron when you put it, before I put it into the water? What was T, let's call this 2 and this 1. What was T1, the temperature of the iron? Iron's Fe, by the way. Before you put it into the water. Just before. I'll just put it like that. Okay, so see if you can solve for that. In, see if we can find the initial temperature of the iron, knowing that when we threw it in the water that it heated up the water by 2 degrees. Isn't this calorimetry or something?
Yeah, we can do the plus.
So, just so we can finish up, who got an answer? What did you get?
492.3.
Thousand.
So that'd be, a little over 200 Celsius above freezing. So pretty hot. All right, let's see if we can get that. So we're going to take, so I'm just going to write that, start out with this. And I'm going to say that C1, T final minus T1 is equal to negative C2, T final minus T2. Factor through the minus sign, minus, plus, and what am I interested in? Well, I'm interested in this T1. That's the initial temperature of the iron. So I'm going to bring this over to here and then put in another minus sign. So I get C1, T1 minus is equal to minus C1, T final, plus C2, T final, or minus, that's a minus sign there, minus C2, T final, plus C2, T2. Okay, and get rid of those. Put a minus sign on everything, like that, and then divide through by C1. So I get T1 is equal to T final plus C2 over C1, T final, minus C2 over C1, T2. The C2 is still this, and the C1 is still this. And if I plug in numbers, I'll get 492.3. Does that make sense to everyone? All right. Well, next time I think we'll look and see if I add heat to something, how much work can I actually get out of it. That's a very tricky and interesting idea, and it turns out that there's a limit to it. No matter how efficient no matter how good I make the machine, I can't ever get past a certain distance. I can't get the same amount of work as the people that
You're gonna lose it.
First law, I can't ever get it free. Second law says.
No way.
Say it can't be free.